No, that I saw myself in my chest.
Okay, we will wait for the people who went to the toilet, I guess. Well, I think the important people is already here, so we can just start. Well, as you already know, we will change subjects now quite dramatically, and we are going to talk for the rest of the day today of the use of different geospatial technologies for different purposes that might be more or less related to your incoming research in Rota. So anytime I am asked to give an introductory talk about this thing, there's always the issue of finding a good balance between being too basic and then boring some people that perhaps already knows what I'm going to tell, and being a little bit more advanced and then running the risk of some people getting lost at some point. So I usually opt for the first option. Because I think it's better that boring some people, but at least everybody will understand what I will tell you. So I don't know what's your background with this field of geospatial technologies. I guess that most of you have at some point used a GPS device, for instance, but I don't know how many of you have some familiarity with GIS systems. Have you ever used GIS? Do you know what GIS is? Please raise your hands if you. Okay, but not all of you. What about remote sensing? Do you know what remote sensing is? Have you ever used satellite imagery? Okay, some of you will be really bored in the next hour. LiDAR, photogrammetry, do you know about that? Okay, so well, you are quite familiar with that. So I'm sorry about that, but even so, I will just, as I said, give a very introductory talk about these things, aimed especially at giving you the basic information to understand what Jesus is going to discuss later on today. So I will just start by defining what geospatial technologies are and what is within this very broad concept. And then I will be detailing the uses of these different technologies using an approach based on the application of each one of them. What are they useful for? And using this scheme of classification, tools that are useful for mapping, for documenting, for data management, and for data analysis. I will use some examples in order to make the presentation a little more fluid and less boring, so I hope it will be useful for you. Well, as I said, this is a very introductory thing that has the purpose of helping you to navigate this big realm of geographic information science, which is a complex field composed of many different components, and that sometimes can be a bit confusing when seen from the outside or when approached for the first time, because, well, you can get easily lost on what resources should I use if I want to do this thing or this other thing. So this is the purpose of this presentation. Well, the spatial technologies, also called geomatics or spatial information technologies, can be defined as a constellation of things that all of them relate with the collection, distribution, storage, analysis, processing, and presentation of geographic data. I mean, the common point of this big field is that they all deal with geographic data, meaning data that relate to phenomena that can be located especially at some point in the globe. So anything that has a spatial dimension can be analyzed, documented, explored, and so on, using some of these geospatial technologies. It doesn't matter the scale of these phenomena, if they are global or very local. It doesn't matter the nature of this information, if it's historical, natural, cultural, linguistic, whatever. Anything that can be located at some point in the globe can be managed and analyzed using these technologies. So this constellation is composed of many different things. It's composed of methods, tools, technologies that relate to each other differently. And that can be, as I said before, a little confusing when seen from the first time. This is kind of a map of these technologies that more or less are put in the slide in the spatial position where they relate to each other more or less frequently. So, as I said, this can be a bit confusing and overwhelming when seen from outside and from the first time. And a good way to navigate this constellation is to focus on what are they useful for. So this will be as I said before, the pathway that I follow in this presentation. So I will start by talking about tools that are useful for mapping. And yes, the first thing we need to do is to define what is mapping. Well, I guess that all of you are aware of this, but mapping is just locating things in their position in general. And there are two basic ways of mapping, of locating things in the space: absolute and relative positions, right? So there are different tools that are useful for these two different ways of locating things. The most useful tool for locating things in relative terms is the total station. That archaeologists here will know about that, and perhaps some other people also too. A total station is a basic topographic device that is a standard tool for archaeological excavation, for instance. It's a tool, it's a digital tool that allows you to locate, to measure the position of anything with relation to the point where the station is placed, is located. So that's it. It won't give you, it can give you, if you do some operations, but it usually won't give you the absolute position of anything, the coordinates of something, but only the relative position with relation to the place where it is placed. As I said, in archaeology, it's a very common tool, and there will be some archaeological excavation this year in Rota, and I think that some of you will be participating in the excavation to see how the excavations go on. So you will become more familiar with the use of total station in excavations that produce this kind of maps. It's kind of maps that, in this case, is the distribution of archaeological artifacts in a sector. And, well, the lines represent the perimeter of different constructions in the site. So this is the typical use of total station, which is a very accurate method of location because it gives you the location of things down to the millimeter with very little error, but it's a little slow in their use, and it's limited to mapping things in small areas, of course, because it has a limited range and so on. So it's only basically useful for creating maps of things at a very local scales. Then, for absolute position is the absolutely well-known GPS system, which actually GPS is like a metonym for what is properly known as Global Navigation Satellite System, GNSS. GNSS is this technology that allows us to locate anything in the globe based on the position of different satellites. And there are 4 constellations of satellites. GPS is only one of these constellations of satellites. It's the American constellation. But there's also the GLONASS, which is Russian, Beidou, which is Chinese, and Galileo, which is European. This is the number of satellites that compose each of these constellations. So modern GPS receivers usually use indistinctly either of these constellations. Most of them can have access to both, to the 4 constellations. So in ideal conditions, they can have access to very large number of satellites, which increases the accuracy of the position. As you already know, your modern cell phones already have GPS sensors, so you can have the location of something using your mobile phone, but the accuracy of the position changes depending on the device you use for that. So a smartphone has usually an accuracy between 5 to 10 meters, only in optimal conditions. By optimal conditions, meaning clear sky, no trees above you, and a good constellation of satellites above you. So if those conditions are not optimal, then the accuracy can be even lower than that. Which means that locating things with your mobile phone is good if that accuracy is okay for you. If, for instance, you want to know just where in the island of Rota I am, that's okay. But if you want, for instance, to locate with the position of something that is smaller than this accuracy, perhaps a mobile phone is not a very good solution. Handheld receivers like this one here have higher accuracy that can be up to 3 to 5 meters, which is quite okay to locate things that for most of you will be just enough. When you are doing superficial survey, if you, for instance, want to map the position of a tree, might be okay if there are no other trees around. That I mean, if this tree is more or less isolated, that's okay. If this tree is surrounded by other trees that are different to this one, then perhaps this accuracy is not enough for you. Okay. But if you want to map the position where you are taking a sample of soil, that can be okay. So it depends on the accuracy you need. A handheld GPS could be just okay, or perhaps you will need to use a topographic receiver such as this one. The good thing of these topographic receivers is that they can achieve, as you can see there, very high precisions, equivalent to the precision of a total station, even in real time sometimes. I mean, you don't need to, because sometimes you need to take a measurement, go to the lab, and then process the measurement to increase the accuracy. But sometimes you can do that in real time. But the drawback is that they require some training. It's not too complex, but it's just not like having your cell phone and using an app. It's a little bit more complex than that. And the other drawback is that this is, again, a very expensive equipment, quite bulky, and I don't think that you will be able to have one of these available at Rota. Or will you? No. So that's just for you to know that this exists, but in this case, you won't have it available for your fieldwork. So you need to know that if you use one of those other options, the accuracy of your measurements will be this one. So you need to live with that and to know that this is the situation, okay? Well, this is the kind of an example of an application of the use of GPS, of high accuracy GPS, in this case for an archaeological survey around an ancient battlefield from the Roman period in the south of Spain. And this is the kind of information that you can collect using these devices. This is the distribution of different types of archaeological findings that to these researchers have given clues of how this battle happened, where the armies were located, and so on. So, well, it can cover much higher areas than a total station. It is much faster, and if you have if the accuracy of your questions matches the accuracy of your device, then it's a really useful thing for many purposes. Well, absolute position is expressed through coordinates, as you already know. Coordinates are pairs of numbers that express the position of something in the world. That can be like degrees or can be like meters. It depends on the type of coordinate system that you use. But there is also a second important component of any spatial location, which is the spatial reference system. A pair of coordinates by itself won't give you the position of anything in the world if you don't know what is the spatial reference system that those coordinates refer to. This is a very complex realm. This is the realm of geodesy, which deals with defining the shape of the globe, defining the shape of the Earth, and how you locate things in this shape. So I don't want to get into that right now because, as I said, it's very complex. But I want you to be aware that this is very important for you to know, that coordinates are not enough to locate something in the world. You also need to know what is the spatial reference system of those coordinates. And quite frequently, if you are using a GIS system and combining different layers of information, and then suddenly one of the layers is not where it should be, but happens to be like some kilometers away, probably the problem is a problem of a spatial reference system. So just be aware of that. Okay. we won't enter into more details right now, but just be aware that coordinates by themselves are not enough to know where something is located. Well, let's move to tools that are useful for documenting things, okay? By documenting, I mean identifying things and describing the shape and characteristics. And there's a very large range of options within this field of geographic information technologies that are useful for documenting things in different ways. And I will describe very shortly these 5 different options: photo interpretation, spectral analysis or remote sensing, photogrammetry and computer vision techniques, laser scanning, and LiDAR. Well, photo interpretation is perhaps the easiest way of documenting something using geographic information, which is basically looking at aerial images or satellite images and interpreting visually what's going on in that image. It's as simple as that. Well, as simple. It's not really simple in the end, but theoretically it's very simple. And actually, this is something that has existed for many decades now. It's much, much older than the development of digital technologies, because aerial pictures have existed since the late 19th century, the beginning of the 20th century. And in many disciplines, such in archaeology, they have been used to identify, to detect, and to find archaeological traces by taking pictures of an area and looking at what was going on there. The basic principle of photo interpretation is the principle of that viewing something from above gives you a much quicker and easier way to understand a landscape. If you see a landscape from the air, you will be able to understand it much easily and to locate yourself and to navigate that landscape than doing it just on the ground. And I have a very good, I think, which is a very good example here. This is a photo of an area in the Atacama Desert in northern Chile, where I have been doing fieldwork for some years in the last decade. And this picture is taken in an archaeological site. What you see there, this amount of stones, there are part of an ancient field system dated in the pre-Inca and Inca period. And if you see this picture, you really will find very difficult to identify any recognizable over there. If you walk this landscape, you will notice that there are alignments of stones that compose like field plots and so on. But it's very, very difficult to imagine how this is organized. If you just simply see this from the air, everything becomes really obviously clear and straightforward. So this is the principle of photo interpretation. Okay, is that looking things from above sometimes, many times, allows you to understand what's going on in a piece of land much easily and much easily and much quickly than doing it just walking through this area and mapping everything and so on. The same applies to satellite imagery. Okay, this is an aerial picture taken with a drone. This is a satellite image of the same area. And again, there are many things that are very apparent here, and we can quite easily compose a first impression map of the archaeological remains in this area. Okay, like just drawing on top of this, what we interpret visually, what's going on there. Okay, so we have in yellow fields, in these purple color constructions like houses and storage areas and so on. And these dotted red lines are remains of ancient canals of irrigation. Okay. Well, we know that because we have been walking in this area and we have been able to identify how these things look in the images. This is something different than doing remote sensing, properly speaking. Remote sensing deals not with visually interpreting what we see in a satellite or aerial image, but with extracting information from the numerical, from the figures, the numbers included in any digital image. And this is, compared to photo interpretation, a technically complex process. I mean, it's not as simple as looking at a picture and seeing what's going on there, but it involves some technicalities that are not so easy to grasp. Okay, and it's applied in many different fields: biology, forestry, agriculture, archaeology, and so on. Well, what's the principle of remote sensing understood as spectral analysis? The principle is that any picture, any pixel in a digital image, in a picture that you take with your mobile phones or whatever, is composed of three values, has three values: a value of red, a value of green, and a value of blue. That's why most images are called RGB images. Okay, they are any standard digital camera captures information from these three bands, as they are called. Okay, so any pixel has a number that represents the amount of red that is in that specific pixel, the amount of green, and the amount of blue. And composing the three of them together gives you the typical standard digital image. Okay, but red, green, and blue are only a very small part of this thing that is called, the electromagnetic radiation. Okay, electromagnetic radiation is the radiation that the sun emits, and that is differently absorbed and reflected by anything in the world, by anything where this radiation impacts objects, trees, people, or animals, or whatever. So standard digital cameras, as our own eyes, are only able to view, to perceive a very small portion of this electromagnetic radiation, this very small portion here, where the red, green, and blue are. But the radiation is much longer than that, okay? And there are other parts of this electromagnetic radiation that we cannot see, but we can feel, like the ultraviolet radiation, which is what burns our skin in the summer, okay? We don't see it, but it's there. There are some animals, for instance, that are able to see a little bit in the infrared or the ultraviolet part of the spectrum. So they can, for instance, view the temperature of things, okay? Something that we cannot see, but we can, it can be viewed by some animals. So there are some sensors that are able to capture information not only in the red, green, and blue part of the spectrum, but also in other parts, like for instance, the near infrared, which is this one here. This particular satellite image has information in these four bands: the red, the green, the blue, and the near infrared. And these other bands are very interesting because they can give us information about other properties of objects other than those properties that we can just see. For instance, the near infrared radiation is very much influenced, when we speak of temperature and humidity, is very much influenced by the humidity of things. Things that are very humid reflect very more near infrared radiation than things that are very dry. Okay, so if in this image, instead of seeing red as red, green as green, and blue as blue, as our eyes can see that, we can ask the computer to show us near infrared as red, green as green, and blue as blue. And we can have this image. This image is an image of the different humidity in this particular part of the world. So areas in red are areas with more humidity, and areas we have lower hues of red are areas where humidity is much lower. So this is the basics of remote sensing. Okay, it's operating with the spectral information that is inside the pixels of a digital image. This particular satellite image only has four bands, four levels of information: red, green, blue, and near infrared. But there are others that have like 10, 12, or even thousands of bands of information. So they can be very useful for detecting things that are not detectable at simple sight. For instance, in this particular case, these people have used satellite images to highlight the presence, the possible presence of things buried under the soil, because the existence of those things buried under the soil affect properties of the surface of the soil. The soil is probably thinner in those areas, so it retains less humidity. So with proper processing of satellite images, this greener areas probably are reflecting the existence of archaeological remains beneath that. Okay, this is a typical use of satellite imagery in archaeological survey, and satellite imagery and remote sensing is has been very much used in things like forestry, agriculture, and so on, to automatically map different types of land cover. This is an example I just found yesterday about a study in Fiji, where these people, just the purpose of this work, this is a very common approach in remote sensing, was to produce a map of different land uses in this island. So this is a satellite image as in the visible spectrum, as we would see this area if we were flying over it. And by processing the different qualities of different pixels, you can automatically create a map of different land uses. Well, the legend is hidden here, but this will be forested areas, it will be cultivated, this will be constructed, this will be water, and so on. So this can be done by automatically processing the information contained in those pixels. And you can do that at the level of different land uses, like constructed, cultivated, and so on. But also, especially in the recent years, there have been successful experiences even in discriminating different types of trees, for instance, using remote sensing. This is an example, again, in the Pacific, where these people have been useful to tell apart coconut trees from other part of trees. Because, as I said, every object reflects and absorbs differently the electromagnetic radiation, and these differences is much more accurate, strong between very different things like trees and concrete, for instance, but also different types of trees, different types of vegetation absorb differently and emit differently electromagnetic radiation. So using more detailed forms of analysis, you can even be able to discriminate different types of trees, and this will be one of the avenues that Fasil will explore in his particular research. So there are different software tools to do this kind of processing. These are one of the most commonly used, just for you to know these names. And well, if you heard about AirDAS or SNAP, you know that there are tools for doing these kind of things. Okay. So another tool for documenting things is photogrammetry and, well, computer vision techniques, which are somehow related. In this case, the purpose of photogrammetry is not discriminating things with relation to each other, but documenting the geometric form of things, documenting the 3D volume of anything based just on optical principles, on the principle of stereoscopic vision. I suppose that you already know that we see the world in 3D because we have two eyes, right? If we just had one eye, it would be for us much more difficult to see the world in 3D. And there is a quite funny experiment that I usually do, and we can do it right now, just to check this, and you can use them with your kids and so on. Just pick like a pen or something like that, or a pointy thing. Hold it with your less useful hand. I mean, if you are right-handed, hold it with the left hand and the opposite. And then close one of your eyes, doesn't matter which one, and with the other hand, just try to touch the tip of the thing.
But looking at the pen.
Looking at the pen, yeah. It's not that easy, isn't it? If you do it, but if you were successful, perhaps you were successful because you did it very slowly, right? Try to do it quickly. Okay. If you do it with your two eyes open, it's just a piece of bread. It's very, very easy. Okay. This is because our brain reconstructs the 3D shape of the world by combining the slightly different image that each of our eyes is producing. We don't see exactly the same with the two eyes, you know that. So the brain reconstructs the 3D impression of 3D is just the depth of things, is how far or close things are related to us. Okay. So since we have two eyes, we can do that. So photogrammetry does exactly the same by using at least two slightly different images of something, it can, the dedicated software that does this, can reconstruct the 3D shape of things. If we do this with, instead of just 2 pictures, with many pictures, things become much easier and much more detailed. Okay, so with photogrammetry, we can just reconstruct the 3D scenarios of anything from small objects to field structures to large landscapes. It doesn't matter the scale of things. Okay, and well, this was an example. I have a couple of samples here. We could open them and watch them, but you will find lots of examples in our website, which is called Sketchfab, which is dedicated to people to upload 3D models of anything. So you can just browse things of different nature, different things, very, very, very different. This is, in archaeology, it has been very much used to document things in superficial survey, like this one here, or in archaeological excavation. This is the excavation of a trench from the Civil War in Spain, which has been documented using photogrammetry. But as I said before, if you, instead of using pictures taken from the field with a mobile phone or a digital camera or whatever, if you use pictures taken from above, from UAVs or from planes or whatever, you can produce 3D reconstructions of entire landscapes. Okay, and this becomes at some points much more useful when doing archaeological research or other types of research. In archaeology, it's much more useful when vegetation is sparse or absent, because you can see the material remains over there. But if you can use this, for instance, to recreate the 3D shape of a canopy of a forest, for instance, if you are interested in that. Okay. This is, again, an example that we did in the same area, that the sample I showed you before, in northern Chile. This is an ideal area for doing this with archaeological purpose, because there's almost no vegetation there and everything is visible on the ground. So you can produce this 3D image of this area, 3D reconstruction, in this case using more than 2,000 pictures. And this, you can achieve really high details, like in this case here, you can see a detail of the ortho image produced with this model. You can identify every single stone composing the walls of the site, and even these grinding stones over there. So you can reach very high details. So the thing with photogrammetry is that you will reconstruct the surface of things as they are, as you can see them on the ground. Se fue. Pásame la siguiente, por favor. Ah, ya está, ya está. The good thing about photogrammetry is that it's very user-friendly. There are tools like Agisoft Metashape that have a very straightforward pipeline. You just basically enter your pictures, click a couple of buttons, and get your 3D model. It's very easy. It's not as easy as that, but it can be really very easy. You only need a digital camera to produce a 3D model, no more than that, so it's very accessible. Okay, but it has its limitations, and basically the limitation is that you only can map what you can see. Okay, if you have trees and you want to document what's beneath the trees, photogrammetry is not an option. For that, there are other options, like the 3D laser scanner that you probably know about it, which is, again, a tool for volumetric documentation, but it's based on the emission and reflection of laser beams from a machine like this one here, which is a 3D laser scanner, quite conventional, in this case, used to document the internal shape of a megalithic chamber, of a burial mound here in Galicia. And laser scanners produce this kind of results, what are called point clouds. Okay, very dense point cloud. This is not a picture. This is a, well, it can be seen here. This is a very dense number of points, each one of these points with a 3D position. So the combination of all of these points produces a 3D image of the object or objects that you were pointing at. Well, again, used in archaeology, well, for many purposes and so on. But the interesting thing is that if you put this laser scanner into a plane, or on a plane, then you enter the realm of LiDAR. LiDAR is basically a laser scanner that is transported by an airplane and a drone or a helicopter or whatever. And that has been used to create 3D documentation of large parts of the world. I think there's many parts of the world that have been already covered by LiDAR flights, and most of the modern cartography is produced using this kind of technology. The good thing about LiDAR, especially when compared to photogrammetry, is that LiDAR has an ability to penetrate vegetation in a way. I won't go into this detail, but with LiDAR, you can not only document the surface of things as you look them from the air, but also, in some cases, what is lying beneath those things. This is, again, a typical example of the results of a LiDAR flight over a rather small area, in this case, where the first thing that you document is the surface of things as they are, in this case, lots of trees and vegetation. But, as I said, LiDAR can penetrate vegetation, and you can remove that and see what's lying under the canopy. So that's why LiDAR has been especially popular in archaeological survey, because it allows you to see things that otherwise would be really difficult to see. Well, what you can see there is an Iron Age hill fort with the ramparts, the ditches, and so on. Well, it produces, again, these point clouds with very high densities. They can be like thousands of points per square meter. It's very costly, but it's being growingly available. And the good thing is that today we have also LiDAR sensors that can be mounted on drones. So you can have your own small-scale LiDAR device. We have one here at the INCIPIT, and many other institutions do have ones. But the drawback, again, is that not anyone can fly one of these drones. You need some special trainings, but, well, at least you don't depend exclusively on external sources, and you can, under good conditions, produce your own LiDAR data. There's an almost full LiDAR coverage for Rota. I think that probably Jesus will use it later on today. I say almost full because there's a small sector in the south of the island that there's a gap there. I don't know why, but it's not there. But these data are available for download, and it can be really useful for most of you. For Fossil, undoubtedly will be, perhaps also for EDUI, and maybe for some of other of you too. Well, LiDAR has been very popular in archaeology. Perhaps you have come across news like this one here that sometimes appear in the media, National Geographic, things like that, that the hidden city of wherever is discovered in the jungle of wherever, in most cases in tropical parts of the world, like in Central America. And actually, it has been quite a revolutionary thing for the documentation of things that otherwise might take decades of traditional field survey to map all these structures that are lying behind this very dense forest in Guatemala, in this case. But besides that, LiDAR is also a very good tool to give you a more detailed and accurate image of the topography of a site, of how the topography of an area is organized, besides the impression that might be a little bit misleading of more traditional sources like this aerial image here. This is here in Galicia, and this looks like a quite flat area if you look this way. Even if you look at the LiDAR data in the most typical visualization, which is this one, it's called a hill-shaped map, things look fairly flat in general. So there are some topographic changes here and there, basically the roads and things like that, but it doesn't look like a very varied topography. The good thing is that LiDAR data can be processed in different ways, and you can highlight different, you can use different visualizations to highlight topographic variations that otherwise might be unnoticed, like this visualization here, which is called a sky view factor map, which gives you a very different image of this particular topography and highlights, in this case, the existence of lots of artificial modifications in this landscape that probably, when you walk on this area, will remain unnoticed because they have been very flattened out by modern cultivation, but they are still there. I mean, the traces of these modifications, of these ancient modifications, are still there. Or this is another visualization, which is called a local relief map that again highlights things that otherwise will be unnoticed. So LiDAR has a very high capacity of giving us different impressions of the landscape we are dealing with. And LiDAR also can be useful not only to look at the ground and look at the terrain, but also to look at what's going on the terrain, like vegetation. And LiDAR has been extensively used, for instance, to map forested areas or areas with vegetation, to quantify the number of trees in an area, to quantify the volume of potential timber in an area, things like that. So it's not only useful for looking at the ground, but also to looking at things that are on the ground. So we can move to the third main utility of geospatial technologies, which is data management. We have been able so far to map things, to locate things especially, to document and identify many different things. So we have produced lots of special information, special data. The basic tool for data management is geographic information systems. This is where geographic information systems come. It's the basic tool that allows us to integrate all the data produced with any other of the former tools or methods that I have been discussed so far. Okay, it's where we do all the data management, the data exploration, search, queries, and any other thing. So we can use different tools and methods to collect data, but in the end, we are always ending putting all those data into a GIS and using a GIS to combine all those data in different ways. And it's also the basic device for the production of cartography, of maps, which is sometimes kind of a byproduct of GIS, a secondary use of GIS, but in the end is what most people does with GIS is producing maps. Okay, so it's a very important thing, producing maps, in the end, even if it's not so sexy as doing other more complicated and sophisticated things with them. Okay, I will come back to maps in a minute. Okay, well, this is a typical image of an application online, in this case, produced with different special maps and produced using GIS systems. Another good example of an application of GIS for humanistic data is the one that Patricia Murrieta showed us last week in her webinar, all these things with the documents and so on. This is basically a GIS-based application that in that case, again, was uploaded in the internet, and well, it has another user interfaces and things like that, but in the end, it's GIS what is behind that. Okay. As I said, production of maps is one of these most common uses and basic uses of GIS, that is useful in almost any case and for almost any purpose. Okay, even if you are just a basic GIS user, probably at some point you will be producing some maps with GIS. So producing maps is something that requires some basic skills that are highly recommended. It's something, a very typical mistake is producing bad maps with GIS. And producing bad maps is a bad output of the use of GIS, because a good map can make a big difference. I will just show you now a couple of examples in order just to make you aware of how important it is to reflect on how we produce a map and the importance of producing good maps as an important part of the output of your research. I have just selected a few examples of maps that are especially bad for different reasons. In this case, this map is bad first and foremost because it's very ugly. Okay, so that's what most obvious at first sight. But besides being very ugly, it's a very confusing map. It has so much information. It uses so confusing symbols. It has this background, which is a topography, which really doesn't give you any interesting information because you can almost see it. So it's really an example of a very good map that is very misleading because it transmits very badly the message that this person wants to transmit when he or she produces this map. I don't remember where did they take this from. This is a much more pleasant map. It's beautifully designed, it has good colors, it has a very good balance of colors. I mean, it's beautiful. You can even print it and put in as decoration somewhere. But the problem with this map is that it is very confusing in terms of information transmission. A map is a device for transmitting information. This is something that you have always to bear in mind. So it's very important that the information you want to transmit is clear and is easily understandable. The problem with this map is it combines 3 different layers of information: reading, writing, and earning money. It is supposed to give you an idea of the correlation between these 3 things, but it only gives a very confusing idea. I mean, it's very difficult to extract any information by looking at this map. Okay, so it will be, in this case, for instance, much more interesting to produce 3 different maps for the 3 different things, and then to let your brain to do the visual connections between the 3 of them. Again, this is a map that, well, has some nice colors. It's not so ugly. It's not very beautiful either. But it's, again, an example of a map that is not very good for transmitting the information that the person who made the map wanted to transmit. Basically, in this case, because it's very different, it's very difficult, to tell apart the background from the foreground. I mean, the aim of this map is to show what is called the viewshed, the portion of terrain that is viewed from an archaeological site, which is called a Torreón, which is located somewhere where this white hue is, and is probably here, is the only candidate for being that, but this is not obvious at all. And the area visible from this site should be painted in green, but there's a lot of greens over here. So the area is here if you take a detailed look at the map. But again, it's a bad map in this case because it doesn't make a good job of separating the background from the essential information that is that the author wants to transmit. So this is just very quick examples to show you that good or bad selections when producing maps can make a really big difference. So anytime you want to produce a map, you need to think, what's the information you want to tell using that map, and to produce the map accordingly with that. And besides that, if the map is beautiful, then it's much better, okay? So GIS systems come in different versions. There you have basically licensed tools like ArcGIS, which is the most common commercial GIS system. It was the one that opened the way for the widespread use of GIS like 30 years ago or something like that. But nowadays it's becoming more and more overtaken by free tools like QGIS, which is the one that Jesus will be using in his examples later on, and probably the one that you will be using in the field most of the times, because nowadays it's as practical, or in some cases even more practical than ArcGIS, and it has also the benefit of being free, which is something that is always good. Okay. And we come to the last field of use of this geographical information technology, which is data analysis. That is, again, something that relates to the use of GIS. Because GIS is not only useful for putting data together, creating maps, and overlaying different layers of data, but also to analyze those data. Analyzing as a way of answering questions related to the location of things. So it's not just a matter of putting things together and seeing what's going on, but to formulate questions and to use different forms of spatial analysis to answer those questions. Okay, it has lots of possibilities, and it can be more or less sophisticated and more or less useful. And the benefits of using GIS as analytical tools are basically these 4 points that are listed over there. GIS allows you to automate calculations, to automate analysis, to analyze large amounts of data very easily and very automatically, to do very quickly and easily things that otherwise might have taken you lots of time and of effort. It has also the benefit of integration, of comparing different data sets and comparing one to each other, seeing, exploring, for instance, the influence of one data set into other data set or correspondences between different, the spatial distribution of different things and so on. The third benefit is the benefit of modeling, the ability to create ideal conditions to test hypotheses, not only exploring data as they are in the world today, but also creating data under different theoretical conditions to construct hypotheses and see what's going on. What if this area were this or that way? What if sites were not only where they are today, but also in this other area today? You can do these kind of things with modeling in GIS. And then it has the final benefit of quantification. GIS are digital tools. Digital tools imply that they're based on numbers. So anything that comes into a GIS is based on numbers. There are always numbers behind that. So this is an intrinsic quality of GIS. And it allows you to express results in measurable ways, which is usually a more robust way to express observation than seeing, I believe that this is bigger than this. Okay, this is different from saying, well, this measures 10 meters and this measures 200 meters. Then I believe that this is bigger than this. This is a different thing. So I have just a final example of an archaeological example thought to illustrate these 4 benefits into a specific case study. It might take me like 50 minutes. How do you feel about that? Do you think it's okay, or otherwise you can stop here? I mean, no, we can see. Okay.
Enough time to go to the
Sorry?
I need to go to the rest.
The restaurant, but it's only 15 minutes.
Do we go ahead? Okay. Well, it's, as I said, it's an archaeological example because I'm an archaeologist and this is the field I know the better. And the idea of this example is not to focus on the example itself, but I would like you to think if this framework of analysis, this type of analysis, type of questions that this analysis asks, and the type of analytical tools that it uses to answer the questions could be useful for any of your particular projects at some point. I mean, if thinking, especially in these terms, can be useful for you at any point. The example is a very tiny, a little thing. It's trying to understand the locational decisions taken by burial mound builders in the past in a particular part of the world, in Mongolia. And this is a very typical question in archaeology for a very long time, in what is called spatial archaeology, which is a branch of archaeology aimed at understanding why people did things in the past, where they did it, why people lived in that place and not in that other place, because that can inform us about social decisions, social organization, and things like that. So that's why spatial archaeology exists since many years ago. So the question would be, why did these people build the mounds where they built them and not elsewhere? This is the study area. It probably couldn't be more different to Rota than it is. It's in the highlands of Mongolia. It's around this big mountain, which is called I thought it was in the title of the journal, of the paper. Ingbold-ul, I don't remember. I've never been to Mongolia. I just assisted with the spatial analysis to my colleague, Cecilia Dalsovo, who has the person who did the work in this area. It's a very large area, as you can see there. This is geographical scale, very large study area. And it's an area where there are lots of burial mounds like this one here. They are very visible on the ground. They can be of different sizes. This is a big one. This is more like an intermediate one. And sometimes it can be really small or being very badly preserved, so not so very well visible on the ground. The good thing is that, as you can see, this is an area with very little vegetation. So there is a very good contrast between the burial mounds and the surrounding terrain. So the burial mounds are very well visible in aerial or satellite images like this one here. So it's very easy to notice, this doesn't work, the presence of mounds like dots here and there. So this would be an example of photo interpretation aimed at locating things in the landscape. Instead of needing to go through all this very big area and mapping the presence of burial mounds, in this case, Cecilia and her collaborators, what they did was using aerial and satellite images to pinpoint the location of these mounds. It's quite an intensive task because there's a lot of aerial images to review, but it's much faster and efficient than doing this on the field. Okay, so they mapped this number of burial mounds is a little bit over 1,000 mounds. Some of them were mapped during fieldwork, the black dots, but most of them were mapped using these images. So this would be an example of detection. Okay. Then the research questions. We had a very big question why people did build burial mounds where they did, but we need to bring this question down to more specific questions that can be explored using spatial tools. Okay, so the first hypothesis was the one that you can see there. Is there a relationship between mounds and human mobility in the landscape? Why this question makes sense? Because we are dealing here with non-sedentary societies, and for non-sedentary societies, movement is something that is especially relevant, it's part of their daily lives. There's also this long-standing idea in archaeology that artificial elements, monuments, these burial mounds are usually called monuments for some reasons that I won't discuss right now, were used as forms of singing, ordering, and appropriating the landscape in the past. So people were building these things in places that made sense for them, and in order to, well, to transmit some information and so on. And there's also the expected persistence of pathways over times in this area. This is, again, an assumption or a part of this hypothesis. So the hypothesis is formulated over there, as you can see in this italic text at the bottom of the slide. So the idea is to explore if there is a significant proximity of these burial mounds to paths. In order to do that, we already had a map of the burial mounds. We needed a map of the paths. And this map was built using exactly the same resources as the burial mounds, using aerial and satellite images to map the existence of paths that were ranked into different categories, the first rank and second rank. Well, I won't go into that detail right now. So this would be an example of integration. We're going to compare two layers of spatial information. On the one hand, the mounds, and on the other hand, the paths. How can we measure if there is a proximity, and especially significant proximity of mounds to paths? It's very easy to measure the distance between each mound and the closest path. That's very easy to do. And we're going to have a figure like an average distance of whatever, 200 meters, for instance. How do we know if that is significantly low or significantly high, or if it's not? A usual way of doing that in spatial analysis is comparing our data sets with random distribution of points. So we can generate a random distribution of points and compare the distance of these points to the paths with the distance of the mounds to the paths, and see if the mounds are closer to the paths than the random distribution of points. And then we have a more solid basis to say that the mounds seem to be significantly close to paths or not. The thing is that one random distribution of points is by definition random. So it might happen that this random distribution of points is anomalously closer to the paths. So to correct that effect, usually what is done is to create different random distribution of points in order to have a more significant statistical sample. Instead of just using one random distribution, the number of points in this distribution is exactly the same of the number of mounds. So it's 100 and something. Okay, so instead of using just one distribution of points, we can use 1,000 distributions of points. This is an example of automation. Okay, we can automate this process, create 1,000 different distribution of points and measure the distance of every single point in every single distribution to the closest path. So we have a much more solid basis for comparison now. And then we can express the results in a statistical way. Okay, this is a graph showing the distance of the random points of the 1,000 different distributions of 1,000 points to the nearest path. The yellow line is the average value, so you can see that. No funciona muy bien. You can see that most of the points are at a distance of something like 100 meters, more or less, from the path. As the distance increases to the paths, the number of points decrease. And this is very consistent, as you can see. This is the average, this is the first standard deviation, this is the second standard deviation. So almost all of the points fall at some point in this gray line. And we can compare this to what happens with the mounts. And what happens with the mounts is this. This is the distance of the variable mounts to the nearest path. So this gives us a very solid basis to say that there is a significant proximity of mounts to the paths. And this is an example of quantification. Okay. And then, still 5 minutes to go. I haven't finished. One thing remains, one of the 4 points that the 4 benefits of using GIS as an analytical tool remains to be explored, with this modeling. I didn't mention anything about modeling. So, how do we know that the current paths are good proxies for unseen mobility? Because we are measuring the distance between mounts and the paths that exist today. But how do we know that those paths are also the paths that people used in the past? Because mounts were built like 2,000 years ago, and perhaps the paths in the past were different. We started with the assumption that paths are very static in time in this area, but this might be true. It may imply that all ancient paths are also in use today, or most, but not necessarily that all modern paths were in use in the past. So this is where modeling comes in. We can think of a way of producing a scenario that is not based on what is observed today in the landscape, but in the potential that the landscape offers for human action. In this case, we can produce a scenario that tells us where and through which ways people would move in this landscape using standard assumptions, like moving for the areas that are more prone for mobility, that areas that are best for mobility. Okay. And we did this in a different, we're moving to a different area now. This is now here in Galicia, but this is exactly the same archaeological problem, measuring the relation between burial mounds and ancient mobility. This is a much smaller area for different reasons. I won't go into that right now, but it's again the same scenario. So the question is the same. And in this area, in this case, we relied on, there's many different possibilities for creating this kind of scenarios, for creating ideal maps of connectivity in an area. We used one tool which is called Circuitscape, which is a tool that was developed in ecology for some people working in ecology to model the most likely ways of movement of animals in the landscape. In this case, it's an example of application of Circuitscape to model the expected routes of mobility of one particular type of tiger across this area. So this is a theoretical model. This is not an observation of where the tigers were moving across, but what could we expect that they are moving based on the physiological characteristic of the tiger and on the characteristic of the terrain. So we know that tigers usually walk in areas that have this kind of slope, that avoid forests or whatever. So you can use all those theoretical data as input and create a theoretical model, an ideal model like this one. So we did the same for this area and created this model of potential human movement across the landscape. So the areas in yellow are those areas that where one might expect that people were moving across when exploring or were traversing this landscape. Okay, so this is again, this gives us a very different approach to the problem than using modern paths to explore this question. So this is an example of modeling. Okay, it's like kind of a very abstract thing, but it's very common and useful in spatial analysis. Well, again, we can quantify this, and we can see that this is the histogram of this image here. So this is how the values of the model are distributed. The numeric values doesn't matter really, but you can see that there are a lot of areas with more or less average conditions for mobility. And as we move here, the number of pixels decrease. So this will be the areas that are more expected to attract mobility. Okay, so there are very few positions that are very extremely good for mobility, and there are a very good large number of positions that are so-so. Okay, and the blue lines are the burial mounds that are located in this area. So as you can see, most of the burial mounds are precisely located in the best areas for mobility. So this gives us, again, a quantifiable assessment of this question that is based not, in this case, in the actual conditions of the landscape today, but in the ideal, in the potential allowances of this landscape. This is the term that is usually used in spatial analysis. Well, I had some other things here, but I will skip them. And I think that's all. Okay.
Thank you so much. So, are there questions? No?
I have one actually. For the theoretical modeling what this is written, and how do you avoid like certain biases that you might have about what would be, for example, a good area for movement? Like I think what we saw on the first day, for example, about how we would assume nobody would live on a very steep slope because it's an assumption that we have, and then the archaeological evidence proved otherwise. So how can you account for those things with this theoretical model?
Yeah, that's a good question. Actually, these kind of models, in this particular case of models of movement, are based on energetic consumption when walking. So you are expecting, or you're not really expecting that. You're modeling where people would move through if they were minimizing the effort to move. So you can then, but then after that, you can interpret or assume that this is what is expected to have happened in the past, but you don't necessarily need to do so. The result of this analysis tells you, no, not that barrows were built where people were moving in the past, but that mounds were built in the areas that had the best conditions for movement. Okay, so then the interpretation might be that this implies that people were moving through these areas and so on, but this is like something that comes after that. Okay.
So, any other questions? No? Then you have to go for lunch very quickly because we're a bit late. But I want to give you an assignment to close the training at the end of the day, which is, you know, because you have read the proposal, that we have insisted in the proposal that we have a historical perspective. In every one of the disciplines and every one of the doctoral dissertations that we are producing in this project, we have a historical perspective, which is fair. So I would like you to think from your point of view, your research, how would you define or how would you conceptualize or apply this historical perspective?
Could you maybe explain what the historical perspective is?
Yes, that's the point. I don't want to explain that.
Okay.
That's my interpretation. And I want you to think about it, and then maybe we can discuss this briefly afterwards. What is history for you? What do you think, what comes to your mind when you say history? I am interested in hearing your notes myself. And so please just briefly, right? Because you don't have to, no, not very long, but just briefly, what do you mean by history when you are thinking of your research? Yeah. And now I have to go pick my children, but then I will come back afterwards. So see you later.
Whenever you will be back from. Yeah, what's that?
Three?
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 Eh?
I think it's 3 hours.
Quando podáis.
Porque entiendo que tardarán en darles de comer bastante, así que...
Claro.
They're staying for free.
Free-ish.
Yeah.
Free-ish. I think it's doable. Part of the very maximum short for.
We'll take a Dutch lunch, not a Spanish lunch. Quick.
No way.
Para todos, ¿no?
Sí.
Jesús, ven un segundo. Ahora, ya que vas a comer con ellos, ¿tiene hambre?